thank you to the Acceleration Consortium for funding this idea. And I'm going to talk through this work. It's going to be a different talk than some of you may have heard before. If you've been to Acceleration Consortium events, this is not a technical talk. This is really, as Brandon said, rooted in the social sciences. Just a quick show of hands for those in the room. How many people have no idea what a self-driving lab is? Okay, so pretty much we have that vocabulary in common. I just wanted to make sure I wasn't going to have people going, I have no idea what a self-driving lab is. I'm speaking a little bit to the converted. Okay, so I'm going to start with my journey to the research question, which is going to be a little bit of a quick synopsis of my, my career and some of the questions that came up for me in my career. And I think it's important to sort of situate this research in, why I'm asking the questions that I'm asking, what's my perspective as I'm coming into this. As you'll hear, I was not trained as a social scientist, but I have sort of learned and have working now with social scientists to ask social science-based questions. We're then going to get into, I'm talking about sustainability. What do we mean by sustainability? What are we talking about in this research? Then we'll get into the actual methodology that was used in this study, go through some of our emerging themes. As you'll hear, this is very much work in progress. So we are really just starting to kind of articulate what we're learning. There are some patterns that are starting to come out of those emerging themes, and then future work. And one of the reasons I'm really excited to be talking to all of you is that future work may involve some of you. I'm hoping to spark some of your curiosity around either collaborating on these questions, being interview subjects in the future on these questions. So hopefully as you're listening, you'll be thinking about what resonates with you and where you like, no, I don't see it that way at all. Listen to that because we want to hear from you. Part of presenting this work is to sort of get a sense of whether or not we're on the right track. Okay, so I am an engineer. I'm an engineering chemist, and this is a picture of the interfacial nylon polymerization reaction that I did in high school. And this got me really excited about material science and this idea that you could engineer polymers by thinking about their chemistry and also by thinking about the way that you process them. So that kind of geeked me out in high school and got me to go into engineering chemistry at Queen's. I then went on and did my doctoral study. I kind of went deep. I went into phys chem, and I was doing gas phase reaction kinetics. This is not me, but this is the kind of setup that we would have had in the lab back at Oxford, early 90s. And one of the reasons that that's relevant is that the work that I was doing was measuring rate constants for stratospherically important reactions. And the reason we were doing that work was because the Montreal Protocol had just been signed in 1987. And we were interested in sort of feeding reaction kinetics into the models that people were building to understand how the ozone hole was going to recover from the forever chemicals, the chlorofluorocarbons. So chlorofluorocarbons, as I'm sure you all know, were making their way up into the stratosphere. There was sort of creating this chemical soup that was attacking ozone, and they wanted to be able to model what was happening, look at that recovery, and also be evaluating the alternatives that were being developed to replace chlorofluorocarbons as they were being phased out. I then came back to Canada and went back to material science, working for the Xerox Research Centre of Canada out in Mississauga. The research center did the materials research for Xerox worldwide. And the program that I was working on was this environmentally friendly toner. I'm going to talk a little bit about this project, partly because I think it sets up some of the blind spots that we often have when we do this work. So EA toner was emulsion aggregation toner. The conventional toner is, and toner is just the stuff you put on the page when you print a page, kind of melts this plastic into the page that's what your ink is. And so the conventional way of making toner was to extrude polymer and pigment and then grind it up into little tiny pieces. That's what you see in the micrograph on the left, right, whatever it is. And that was not a great process. It was relatively energy intensive. It didn't have a lot of great control. And so the idea with the emulsion aggregation toner is that we would run an emulsion polymerization to make a dispersion of our polymer, and then we would aggregate that dispersion with a dispersion of pigment and anything else that we wanted to put in, and we would have really good control kind of building up this toner And it was much less energy intensive to do it this way. And because we could control the size and the shape, it also meant that we were using less toner on the page, and it was a more efficient process in the machine. So we were using less raw materials in the printing process, and generating those raw materials was more advantageous from a greenhouse gas point of view. The other thing that we really believed about this was a water-based process, chemical process, and so therefore it was also environmentally friendly, unlike some of the other competing processes people were playing with that were solvent-based. I had the good fortune to come in to work on this project from relatively early in its development all the way through to putting it into manufacturing. And when we were getting ready to put it into the manufacturing plant, we were working with our colleagues in Japan, where the first one was going to be built. And they said to us, what about the water at the end? What happens to the water at the end of the process? And we said, oh, don't worry about it. It's just got a little bit of soap in it. It'll be fine. And you can just put it in the river. And the Japanese said, not in Japan, you can't. Turns out you also couldn't do it here. We had such a blind spot that we kind of had been thinking about this process entirely as what was in the plant, and like so many people, ignoring what happened when something left the plant. And given that we were so convinced that we were being environmentally friendly, this was particularly embarrassing that we had missed this step. The good news was that it wasn't that difficult to solve the problem. It was quite easy to clean up this material. It wasn't toxic. It was relatively straightforward to fix. But I tell this story because I want to kind of come to this with some humility. I think it's very easy as engineers and scientists to be so focused on the problem you're trying to solve that you kind of miss the downstream impacts. And when I went to work at Hatch in 2008, Hatch serves the mining community. And of course, the mining community is full of examples where people have these unforeseen consequences. This is an image of a phosphate tailings pond in Florida, not dissimilar to many other tailings ponds in the mining industry. You think about the oil sands, where people have sort of said, we'll deal with the water, we'll deal with the wastewater later. And ultimately, they discovered that these things sit there as giant environmental liabilities. And we were working on this problem because the Environmental Protection Agency had said to these companies in Florida, you have to close these down. You have to clean these up and shut them down because the environmental liability is too great. The sinkholes and breaches tend to show up in these things and then release this very inorganic soup into the Florida environment. And of course, we have lots of examples of these sorts of disasters where we haven't thought about the toxicity or the sort of the wastewater as things go out. We haven't taken a more holistic approach. Because I started working in this, or this was one of the first technologies I worked on when I moved to Hatch, I ultimately ended up running the water business for Hatch and serving municipal clients as well as mining and other industrial clients. And one of the things I got really obsessed with was how do we kind of create a more holistic way, a more integrated way of thinking about these problems. And so we would try to gather different disciplines around the table to try and come up with a better way of approaching the problem so that we were polluting less water in the first place, dealing with it and cleaning it up, and then ultimately meaning that it wasn't going to kind of kill the project or kill the plant. And that included thinking about how were we interacting with the communities that cared about water around us, especially when you think about the Canadian North, Indigenous populations that have had really historic, real wrongs done against them in terms of water and pollution. So all of that to say, it was a great industrial career. I learned a lot, and I brought this perspective with me when I came to the university for all the reasons that Brandon talked about. I lead an organization called Truce I Lead. It's part of the engineering faculty, and we study how engineers lead and learn to lead. So we are asking sort of social science-based questions around education and the learning process. But all of this is this idea that we want to help engineers to be able to sort of bridge the technical with the social, to be making sure that they are able to influence change, do the right thing, act ethically. And one of the areas I've gotten particularly interested in is sort of bringing that. How do we bring some of the sustainability things that we all know we are supposed to be doing into the decision-making and research process that we practice as engineers? And so all of this brings me to 2023 when I came to the Accelerate conference. And I was really excited about the Accelerate conference because it spoke to materials design, which is sort of where I started. It was cool robots and artificial intelligence, so that sounded kind of intriguing. But I was also really impressed that there was an ethics stream and that this idea of thinking about how are we doing this ethically was part of the agenda. And so I dragged my colleagues from iLead who are here today. We went to the conference together and listened to the conversations. And what really struck me as I kind of started to understand more about what was happening was that it was a very noble pursuit. And there was a lot of talk about going faster, but I wasn't hearing as much about sort of doing it differently as well, sort of reinventing the way, the sort of the questions I've been thinking about from how do we do this work, how do we integrate sustainability? And I remember going to Murphy's talk where she talked specifically about sort of social justice and environmental justice. And it was really clear that there was sort of a bit of a disconnect between the way that the engineers understood their role or the chemists understood their role and the way that the maybe social science and STS scholars looked at this problem. There was a bit of a bridge that needed to be built. And I know that is being built through the work that's being done in the Acceleration Consortium, but I thought maybe we have a contribution to make at iLead. And so that led us to the research questions. These are the questions that went in with that seed grant. The first question was, how well are social, economic, and environmental considerations currently being incorporated into SDL activities? How might sustainability constraints be integrated into the rapid development cycles of SDL architecture? What collaborations, knowledge, and tools do researchers need to identify and address these design constraints? So to answer these questions, we assembled an interdisciplinary research team. So I was the PI, bringing sort of my engineering background, my materials knowledge, but also my more recent forays into engineering education and social science research. Andrea is my senior research associate, and she brought her expertise in social science methodologies to help us frame this work, adult education, but she also brings this great knowledge about the social economy and sustainability. So she asks really different questions when she's looking at this problem. Yifan Liu was hired specifically for this project. He's here as well. And he comes out of had just finished his PhD at TMU in chemical engineering and had also worked in nanomaterial production. So he kind of brought that, like, sort of, I would say, the current materials research and coming from that academic way of thinking and approaching this problem. And we pulled him in and made him ask social science questions. And then we've just recently had 3 students join us as research assistants who bring different backgrounds. They have expertise in sustainability, engineering education, and sociology. So again, we're trying to bring people who are going to ask questions differently than I do as we're looking at these problems, because they're going to hear different things in the answers. So what do we mean by sustainability? And actually, sustainability is something that there's been a lot of debate around. What is sustainability? What's the best definition of sustainability? It's quite a broad concept. And so we're sort of basing this on the Brundtland Commission definition of sustainability. Sustainability is meeting the needs of the present without compromising the ability of future generations to meet their own needs. And there's also this idea that there are sort of 3 pillars to sustainability: environmental, economic, and social. And so this paper shows sort of different representations in the way that people are talking about this, that it's not just saying we want environmental friendliness, but also impacts on communities, impacts on social structures, and economic viability and development. Of course, in the materials world, we have the green chemistry concepts that have been around now for many years. And we also, as a research team, we sort of use these as we were entering into this conversation and have sort of been looking at how these concepts are being used. For the most part, green chemistry principles are really focusing on that environmental pillar, though. And so we needed to go more broadly in our questions. And we wanted to look across the whole material development process. So if you think about material discovery, then you move through into the sort of process optimization. How are you going to take this material and make it in an economically viable way? What are the applications that you're developing and those needs? And then what is the end use? And you can think about the user requirements informing the design criteria, informing our scale-up criteria, and our materials property, pulling all of that information back. How are we pulling sustainability into those various criteria as we go? Were the kinds of questions that we were looking for, and trying to map, like, where are we seeing the majority of the work when it comes to sustainability, or the majority of the opportunity, and where there might be some particular challenges. So, like all good academics, we did a literature review. In our first literature review, we looked just sort of self-driving labs and sustainability. There weren't a lot of papers. It was about maybe 3 to 5 that were talking about this. So sustainability wasn't a strong concept in the conversation, at least in the academic literature. We then thought, well, let's forget about the robotics piece. Let's just look at AI, because really this kind of translation of criteria is AI. And so out of that, looking at AI, sustainability, and chemistry, we got down to about 54 papers that are doing sustainability or talking about sustainability assessment using AI. And then we kind of looked more deeply, or Yvonne looked more deeply at them, and found 40 articles that were really looking at sustainability and AI together in a meaningful way. Of those 40 articles, 22, as you dug into it, were sort of mentioning it in passing. There's a sustainability target, it's going to help us to get there. 18 were using AI for the purpose of sustainability. And again, as you go deeper into them, 6 of them are talking about the promise of AI for sustainability, but not really getting into the specifics, not really giving us any hints on how people are doing this. Only 12 were really getting into using artificial intelligence and machine learning to improve the accessibility and efficiency of sustainability assessments. 8 of them were using machine learning for optimization for some kind of sustainability enhancement, and 4 of them were using other forms of AI for sustainability assessments. So all of these papers, with the exception, I think, of 1, were from 2021 and after. So this is a very new field that people are just starting to talk about. And it meant that we really wanted to, therefore, go out and talk to people to understand what was happening, because it's not yet in the academic literature in a big way. So our methodology was interviewing. We purposefully recruited interviewees through the Acceleration Consortium by reaching out to people, also through our own network, to find people who are focused on green chemistry and materials for the energy transition. We didn't recruit for drug discovery just because we were trying to sort of narrow the field. And we also kind of felt that there was a good kind of conversation around that trade-off on sustainability, but just to narrow things. We then as we started talking to people, they started to suggest other people that we should talk to. So we call this snowball sampling, where someone says, oh, this person's really thinking about that question, or you should talk to so-and-so. And so we started to kind of find the people that were working in this area. Ultimately, we've so far interviewed 15 individuals, which I know sounds like a very small number to people who are quantitative. But these researchers are applying self-driving lab technology or they're using AI and machine learning to support this. And they're doing this across the entire material development process. So we talked to people that were focused on materials discovery all the way through to industry and manufacturing. We also talked to sustainability and green chemistry experts. Some of them were also doing the SDL work. And we gathered academic and industrial perspectives. The way that we do this is we go in with a set of questions that we want to ask and we want to learn about, but we call these semi-structured interviews. We get into conversation with people and sort of see where the conversation leads us. So we will kind of follow where our interviewees are taking us. Each interview generates sort of 25 to 30 pages of text. And we then go through a process of coding, not coding like computer coding. So in the social sciences, this means taking the written components, breaking them down into smaller chunks, and sort of describing what we're seeing, pulling out what we're hearing out of these conversations. If there's any social scientists in the audience, we were using more of a grounded theory approach, because there really wasn't a framework or a structure that we could use. We were informed by the literature, but we're really trying to listen to the themes that were emerging. And we did this by clustering these codes into emerging themes. I mentioned before that this is a work in progress, so we have kind of done our first 1.5 passes, I'd say, through this coding exercise. We've now added these research assistants, and we're going through it again. This is like a real art of trying to pull this and pull it down into really coherent findings. And yeah. But these are the emerging themes that I want to share today. So the first theme is we kept hearing that sustainability is primarily being considered in the selection of the application space. So when people are talking about sustainability or thinking about sustainability, they tend to think about, I am doing this thing that is going to help with sustainability. I'm designing a new material for the energy transition, or I'm trying to improve the energy efficiency of a material. Or maybe I'm trying to replace a solvent that's problematic. So there is this idea that I have the target is being set because there's a sustainability piece. The second thing is that this idea of life cycle impacts, of looking kind of outside of the system and thinking about what is the overall sustainability impact, is out of scope for most researchers. The third is that the process optimization stage is probably the most ripe, the most rich place that people are playing around with sustainability considerations. The fourth is the development of harmonized data sets is both the greatest challenge and the greatest opportunity when it comes to sustainability. And the fifth is this kind of third pillar, the social aspect of sustainability, is not very well understood sort of by the people that we were talking to. I'm going to go into more detail on each one of these themes to sort of tease out a little bit more about what we're hearing and what we think is happening. And I'm also going to share sort of an indicative quote each time I go through one of these themes. I'm going to just say, because I know you aren't social science researchers, when I give an indicative quote, what that means is this particular quote really illustrates something we were hearing again and again and again. So it's not that just one person said this, but this quote, I think, helps to sort of give some life and some color to what we were hearing in the interviews. The other thing I'm going to encourage you to do as you're listening to what I'm saying, does this resonate? Does this feel like, yeah, I get that, that's how I feel as well? Or are you like, nope, that's not my experience at all? And be listening for that resonance and dissonance, because that's part of what we want to learn about as we're doing this work. Okay, so our first emerging theme. Sustainability is considered in the selection of the application space, but then it tends to become more of a secondary concern. So sustainability informs the goal. I've already alluded to that. Performance and economics tend to be the primary consideration. And this is because to disrupt a technology, to sort of substitute in a new material, you often have to demonstrate improved performance to cost ratio. You're not going to pay ridiculously amounts more for a slightly improved performance. And so this idea of constantly trying to come up with something that makes economic sense as one of the really important, as just as important as the sustainability driver or performance driver is always true. The one place that this might be disrupted is regulation. So regulation, when regulations are changing, often that will drive this sort of pressure. And we heard from people about, people are scrambling, trying to find ways to replace PFAS in applications. It's expensive, it's difficult, but there is this sort of hard stop on using PFAS. And so that pressure is really getting people looking at that particular problem. And generally, when we spoke with people, this idea that they were focused on the target application meant that down the road, we would look at the sustainability or the life cycle impacts of the solution. And so interview 3, very honest articulation of this. I guess I don't really focus on incorporating sustainability into the manufacturing or in the materials. That's my honest answer, that I find that would complicate things, at least for me, in terms of the ability to design a material that works well in an application that is really important for sustainability. So I have this target, I'm trying to find something that works, then I will do the evaluation of, is there a new problem? There's some opportunities that we were hearing about here. Generally, of course, everybody wants to do the right thing. Everybody was broadly aware of green chemistry principles. They want to do the right thing, but they really are looking for tools that can help them to do it. So one of the reasons that interview 3 was talking about that sort of, it would complicate things if I had to think about sustainability while I'm doing this work, is that there aren't easy tools to do that. And so we'll do it later. Recognition that identifying sustainability challenges earlier would be helpful. So if we could do that, that would probably save us spending a lot of time developing something that ultimately is not going to go anywhere. And screening for sustainability in particular could be effective. And so this is a quote from interview 13. We think it's important and useful because we have a lot of projects that are like high throughput combinatorial projects or AI materials discovery, or 10,000 or 100,000 candidate materials. And then you're looking for ways to filter them down and turn that into at most 100 experiments or even less than 100 experiments. And if you can start to do that with incorporating some sustainability concerns, we think that's worth it. This was an industrial lab. Okay, the second emerging theme was that assessing life cycle impacts is out of the scope for most researchers. And this really came down to sort of the reality of doing academic research or being a PhD student. It's often, you're trying to advance the science. You're trying to answer a research question, and trying to make the scope too big just becomes too difficult to do. And so people, again, while they may be broadly aware and may care about it, they're trying to answer this one question. Related to that, we often don't have enough information to evaluate the life cycle impacts. So for example, the manufacturing process may not be known yet. You may be coming up with a new molecule or a new concept for a device, but you don't actually know exactly how that's going to be made. You don't have access to that information. Even if you did, running life cycle assessments and techno-economic assessments is very difficult, it's very specialized, it's very time consuming. And so it takes very specialized knowledge. And to that point, many people point to the fact that in companies, there's often sort of specific departments that this is all that they do, is sort of run these things. And so how, as a PhD student, can I possibly sort of have access to this sort of information? So interview 12 says, one of the main issues is that the tools and expertise for LCA and TEA are just like, it's like you don't just sit down and click a couple of buttons and you have it, right? They take a ton of work and the tools are not readily available. And so there's lots of effort or emphasis being placed in developing more user-friendly software for community use to be able to actually conduct TEA and LCA more readily. So we would love to do it, but it's just not there. But there's opportunities here. So first of all, the good news is that artificial intelligence and machine learning more particularly make multi-parameter optimization possible in the first place. You can consider more things, and people are open to that idea of how do you add more parameters and into your Pareto fronts and sort of optimize against them. In terms of things like life cycle assessment, tools are being developed and data sets are being built. And so this is interview 11. The target is that what you say is not possible, when you say there are too many routes to calculate with LCA, is possible because you do it with an algorithm and the model is sufficiently fast so that you can go through thousands of routes in a matter of minutes, and that gives you the LCA results. So that's the target. You don't stop because it's too big. I mean, that's the whole reason why you're doing AI, is that you're able to deal with such massive problems which you couldn't do before. So we're not there yet, but people, interview 11 and others who we talk to, are specifically working on this problem. Process optimization stage is ripe for incorporating sustainability considerations. I think I used to work in process optimization, so maybe I got especially excited when we were speaking to people that were working in this field. But I think what really struck us about this is that the sustainability piece is not just thinking about the new materials, but the greener routes to make them. And people are thinking about this in this space because, especially when it comes to things like energy and a greenhouse gas, they're conscious of this and they're thinking about that. And there are opportunities to optimize synthesis processes or formulations for sustainability using things like temperature, pressure, solvent selection. So people talk to us about these things. And there were great examples where people had done this. The challenge is that AI only does what it's told, and so you need to be really thinking through very carefully what it is that you're trying to optimize, what is the target. And weighing the parameters is a design decision. So do you have that information? Who sets those design parameters? Who sets those balances? And so what we often heard as we were speaking to people thinking through that materials development process was sort of the earlier that you were, the more it was about providing information. The later you were in the process, then you might start to sort of influence the decision making, and you're sort of setting or weighing the parameters. So interview 6 said, we had a process in which we basically had to maximize for one of the products and then minimize all the side products. But for example, in this case, one of the side products was very easy to get rid of. So they said, you know what? I don't care if the solution that I'm looking at is not a minimum for this one side product, because this one I know I can get rid of very easily, but for the other two, I need them to be at least 0. So in that case, they would rather not work at a higher yield that requires them then to add an extra step to eliminate or separate those compounds. So this idea that they took a yield hit to simplify the separations, which were also energy intensive and expensive. So having that kind of holistic view of the problem, you can start to weigh these different decisions. And interview 6 would argue that is very much the role of the chemist and ultimately the people working sort of on the industrial scale. Lots of opportunities here. AI and machine learning can help to pull information from across different disciplines to assist and accelerate development, and people are working on pulling these different pieces together. Automation, of course, can help standardize techniques. As more information does become available, we can be weighing more parameters, and so that's exciting. Education is really needed, though, to help students to think through these trade-offs and chemists as they enter into industry. And informing materials discovery with scale-up considerations is also something that we heard, that the process chemists would really like the materials discovery people to be thinking about some of these things that are going to make scale-up difficult for them. So if we can find ways to sort of translate the requirements back further, that also will be valuable. Interview 5 says, and then the second is to really teach them about Pareto fronts. There is give and take, right? Like there is the perfect. I want something that's never going to hurt anybody and super, super cheap and comes from recycled feedstocks. But what are you willing to give up? And what do you get for that? And to try and rank those to come up with what is an objective cost function that you can look at and say, that is why I made these decisions. So the practice I try to teach my students is actually this. So this idea that this person that's working in the process optimization is literally trying to think through these trade-offs, which we found really exciting. Emerging theme 4, the development of harmonized data sets is both the greatest challenge and the greatest opportunity for sustainability. And I think anybody working in this area will know that this is something we hear about all the time. How do we build these harmonized data sets? The complexity of chemistry makes harmonization difficult. So just something like nomenclature, different places, different industries calling the same material different things. How we measure a property is also really important information. So some of the examples that were given to us is when you look at biodegradability. To think of biodegradability as a single number, there's like 150 different ways to measure biodegradability, and depending on which method, that's going to change the number that you have. So how do you sort of create the data structure, the ontology to interpret from all of these different sources? The other thing that we heard a lot was access to data. So companies have proprietary databases, but they're not sharing between them. The cost of sort of life cycle assessment tools and databases can be really expensive. Interesting, we heard this from academia, but we also heard this from industry, that people were having trouble getting access to commercial databases. So interview 9 says, we specifically are focusing on LCA and social aspects of the development of new component materials and finding what we have to include into each of these processes. And essentially, that's why, again, ontology is important, because each group is using different types of inventory data for, let's say, automotive manufacturing and different models. then they have to be able to have a sort of harmonized methods so that we can include it as early as possible. So the opportunity is that AI can help. It can be trained to translate between data sets once you have this ontology, and also that self-driving labs bring opportunities to develop structured data sets for sustainability assessments. And there were several examples where people were doing this work. They were generating data for the solubility of polymers, for example, or solvent databases that were trying to fill in the missing pieces in sort of the information that was out there. Interview 11 says, to be honest, that sort of 99% of our time is spent on figuring out what's wrong with our data sets and making them correct. And for that reason, self-driving lab is a solution for many people. Instead of sorting out the mess, figuring out what's wrong with the data you acquired from somebody, you should generate your new data, which is clean, and you've designed the experiments, and the data is exactly what you want. So that's much, much faster in some cases than compared to working with historical data. The fifth theme and the final theme is that the social aspects of sustainability are not well understood. We asked everybody, how are you thinking about social sustainability? And I would say out of the 15 conversations we had, we probably got 15 different answers. People had different interpretations of what that meant. There was really a variable understanding of what the social aspects of sustainability were. And it was generally seen as being out of scope. You know, that I'm focusing on the chemistry, somebody else will be worrying about the social impact. There was some thinking about social aspects of raw material sourcing and other supply chain issues. That seemed to be where people went to first. And one of the biggest challenges, of course, is that artificial intelligence for optimization requires some kind of parameterization. And approaches are really nascent in this area. And so this is a challenge generally with understanding the life cycle or social life cycle assessment of materials generally, and especially a barrier as we come into SDLs. Interview 7 says, so in Europe, that's taking the form of a concept of SCLA, socioeconomic LCA, which is meant to capture some of those important impacts on communities. But every time I've seen a case study done, they kind of go like, oh, here's a hazard assessment, here's the risk assessment. They get a lot of details and numbers about that. And then there's like, here's the LCA, we did this to the ISO standard, and then we did an exploratory SLCA, which means they had absolutely no idea how to do it. They just took their best guess, and here's what they came up with, is that it might be bad for farmers in Cambodia. So it's not well developed, I guess. So this idea that this whole field is just sort of not communicating in a way that we can understand for our work. There is a great opportunity here. The opportunity, I think, is really to bring interdisciplinary teams together to evaluate and inform SDL research, to help better identify challenges and better instruct AI. And the idea of building frameworks and tools to aid decision-making processes and to quantify uncertainties. So there's a lot of, this is a rich area, and people are starting to look at this area. Interview 13 says, I think that goes back to, you know, the importance of providing this information at the get-go, because it's difficult for someone, having seen kind of the cost or whatever of whatever hypothetical material that they're designed to, then to still say, okay, well, this is 1,000 times the carbon emission or 1,000 times the ethical impact, but I'm going to go ahead with it anyways because the performance is so good. I think that's a more difficult decision in that case. I think having this information where you provide that information is very important. So again, how do we pull this through? And interview 13 actually pointed us to some interesting work that's being done out of the National Renewable Energy Lab, where they have actually designed a framework to sort of think through these questions and start to quantify some of these different aspects. And so the 1, 2, 3, 4 is technology readiness levels, or when you're thinking about basic research all the way up to lab prototypes. And they've started to sort of break down what can we think about when. And they're doing things like building like a periodic table of critical minerals and thinking about like a stoplight system for what are the different aspects to consider. So you can start to maybe put that into a parameterized format as you're thinking about optimizations. So we thought that was an interesting find. Okay, so those are the 5 emerging themes. A couple of other kind of higher level patterns that are coming from these themes. And when we're doing this work, we're always looking for convergence. Where are we hearing the same thing over and over and over again? And divergence. Where is there maybe some debate? People are sort of wrestling and coming up with different things. So convergence, we heard again and again that the field is nascent, that this is a really important problem and people are working on it, but it's early days. We also heard when you kind of dig in there, there's sort of an economic pressure that's being faced by individuals and institutions that affect how much scope people can take on. So the people that were able to sort of take on this more holistic approach had more access to information, had more access to manpower, had more access maybe to machinery, whereas other people we talked to were like, I'm just trying to get this robot to work, right? Like, I'm just trying to get this started. I'm an early career. I'm trying to get established. And then you think about things like the cost to access the data, to be able to reach into some of these databases. Also, we heard again and again that this is a multidisciplinary problem, particularly when it comes to thinking about these broader social aspects of sustainability. Where we heard some divergence was there was really differing understanding as we were talking to people on how early we should be thinking about sustainability and how early in the material development process, what was doable and what was even useful. So some people were saying 100% we should be pulling this all the way back, and it's going to help us to make decisions to screen out things. Other people were saying we might miss something if we did that. It's too complicated. It's not worth the effort. There's also a differing sense of how far materials developers should be getting into the sustainability decision-making. So who should be doing this weighing of these parameters? How much was it about providing information versus making decisions? And then how much should we be thinking about the social aspects of the work that we're doing, or how much is that sort of someone else's, well out of our scope? And we had differing opinions from the people we talked to. So all of this to say, what is the way forward? I am personally really excited about this recognition, about the interdisciplinary nature of the challenge, the need to bring different disciplines together to work in a way that is highly collaborative. And I think it's really excellent that my understanding is that there are efforts within the Acceleration Consortium to do exactly that. There's an opportunity to bring these different expertise together to sort of consider the life cycle impacts. And one of the approaches is, I think, to that NREL paper, is to start to identify some of the hot spots. What are the things we need to be thinking about and worrying about as we're developing these various materials? What are the areas of concern that might require mitigation? And what are the areas of uncertainty that require further investigation? And I would love to see a world where we start to think about new research projects that are sort of spinning off to support sort of the advancement of the science. For us, our future work is we are really interested in conducting a few more interviews, especially around some of those more divergent themes. So again, if anyone is interested in participating in the interviews, we would love to talk to you. We will complete our coding to sort of refine and publish our findings. We are also going to be getting an interdisciplinary group together with one of the SDLs we spoke with, and we're going to be sort of trying out this facilitated process of bringing everybody together to sort of map through, think through the life cycle impacts of their particular application, and to sort of see how this works. And from the engineering education point of view, how can we better facilitate that? Are there tools that we can be bringing into that discussion to make that a more effective process? So if you're interested in talking to us about any of that future work, my email contact information is there. So that's all that I have. I want to wrap up, first of all, by acknowledging the people that have done the work. So acknowledge the funding from the SEED grant and the Canada First Research Excellence Fund that funds the Acceleration Consortium. Also the True Style Lead Engineering Leadership Community of Practice that has helped to support some of this research. To the research team, Andrea and Ifan, who conducted all the interviews with me. And did the preliminary coding, and our research assistants, Khadija, Sherry Ann, and Shiri, who are now helping us with this sort of the next going through and digging deeper into the data. And most importantly, the interviewees who have given their time and shared their insights.